We're going to continue on with our second lecture, which will be about variables, many of those being of the continuous nature. Don't all get excited. Yep. Okay, so some of the objectives we'll look at today, I might not be able to finish all these, so we'll find out. But so when we want to understand some of the methods used for graphing continuous data, delineate some of the differences between the use of and the meaning of means and medians, which I'm sure a lot of you guys already know, but we'll talk a little bit more about those. Looking at error and bias, scatter and distribution around, especially means and things like that, especially when we're looking at graphs. Look at the application and use of different types of variables and where they might kind of fit in to different types of research you might be doing. Understand how to quantify scatter by using the standard deviation, as we heard alluded to previously. Then we're also going to look at the Gaussian distribution. I will tell you right now that I will probably frequently refer to this as the normal distribution. I'm going to kind of use those terms kind of interchangeably, so just FYI. We'll also look at the origin of the log normal distribution, how we might use that sometimes, how to calculate and apply the use of confidence intervals of a mean. I'm not going to actually make you ever calculate one on a test, but at least know how you calculate it and know the variables that go into that. And then look at use of error bars in the medical literature. So first off, we'll look at the types of variables that you might run into in the medical literature. So the first thing we'll look at are dependent and independent variables. Does anyone know what an independent variable is?
No, it does not.
It doesn't change? Who thinks it changes?
It can be manipulated in an experiment.
There you go. It can be manipulated in an experiment. So that's what we're going to be doing. So as you conveniently read off the slide. That's okay. I don't fault them. That's why I put it up there. So the independent variable typically is going to be your intervention, or this is going to be the thing that you're controlling for. So say, for instance, I was going to start up a trial to compare different doses of a drug in response to blood pressure. The independent variable is going to be, well, so it could be the different drugs, but say I'm doing one drug and I'm comparing different doses of the drug. That's going to be my independent variable there, right? So what's the dependent variable in that situation then? The blood pressure, right? Because that's a thing that is not, it's going to change based on whatever my independent variable is. I don't have a direct control on the blood pressure. It's just going to do whatever it does based on its relationship to the independent variable. So again, I have control over the independent variable. The dependent variable is going to be the outcome measure, right? So again, looking at opioids, if you're to compare, say, like oxycodone and hydrocodone, what would be, and their effect on pain scale, what would be my independent variable? Yeah, so whether or not they got hydrocodone or oxycodone, right? So that would be it. And then the dependent variable would be? Yeah, it would be the pain scale, right? So changes if it did the FACES scale, whatever it happened to do. So keep in mind, you could have incidences where you would have multiple independent variables. Typically, you'll have kind of one that you're going to be looking at because they get a little too complicated after that. And then you may have multiple dependent variables. So say, for instance, I was looking at blood pressure in the hypertension med example, but I was also looking at things like exercise intolerance or other side effects that could be popping up. Those would all be dependent variables based on the dose of the drug that I'm giving. Okay, so being able to suss out what is the independent versus dependent variable is important, kind of first step for identifying other key parts of the experiment you're looking at. Okay, so then looking at the types of variables that you can have. So the first one we'll talk about is the nominal variable. This one I think nominal, name. When I'm saying that, basically what it just means is that it's a categorical outcome and there's no actual order or magnitude to the different categories. So say, for instance, I was doing a study and I wanted to look at the prevalence of different eye colors in PA students, right? There's not necessarily any inherent order or magnitude to green eyes to brown eyes to blue eyes. They're just different, right? So basically, they're just different names for categories. Blood types are another good example of this. Male versus female is another good example of that. Now, if there's only two nominal variables, like a male versus female, that could also be called a binomial or dichotomous variable. So you can frequently see that, like in yes/no type of type of studies, things like that. So again, no inherent order, magnitude to the differences there. Okay. On the other hand, you can have ordinal variables, which are going to be ones that express some degree of rank, but you'll actually find that the differences between the different rankings are not really going to be all that consistent, right? Or they can change between the different ranks. So say, for instance, I were to do a study and I was looking at quality of health for a patient, right? And so it was a self-assessment survey, and they were able to mark down their quality of health as either being poor, fair, good, or very good, okay? So obviously there's a rank there. Obviously we know that good is not as good as very good, and poor is worse than fair, but how do you actually quantify the differences between, say, fair and good? You can't really, right? So we just know there's an order there, but the magnitude isn't really all that well defined. Okay, you can also think about Likert scales. Does anyone know what a Likert scale is? 0 to 5 are like, strongly disagree through strongly agree. So those are basically just a scale, an ordinal scale, in which you're selecting one option out of that. And again, so say you're rating your professors at the end of the semester, particularly in pharm, and you want to write, strongly agree with everything. That's an example of a Likert scale, which would be an ordinal scale there. And then the last one we'll talk about is going to be the continuous variables. And here you're going to see that this is basically data that is going to be continuous in nature. There is a standard ranking, there's a standard magnitude between them. So say, for instance, we're looking at things like temperature, looking at weight, we're looking at blood pressure, where a 10-point change in blood pressure from, say, 90 to 100 is the same degree of change as going from 100 to 110. Okay? That magnitude is going to stay the same throughout the scale. That makes sense between the three types of variables? Okay. So then we'll break it down a little bit further for the continuous and variables. So looking at the interval variables, these are going to be ones, and again, we probably won't get, in the medical literature, there's probably not a lot of distinction here between interval variables and ratio variables. We'll talk about in the next slide, but we'll just talk about them here just to get the definition out of the way. But an interval variable is going to be a continuous variable. Again, it has equal intervals or distances, but the 0 point isn't really all that meaningful, right? So say, for instance, we're talking about temperature, specifically centigrade, right? So when you get down to 0 degrees centigrade, is that really saying you have no temperature left? No, because you can go to freezing, you go below that, right? So that would be something where the 0 point doesn't actually matter, right? Versus something if you were looking at temperature, say in Kelvin, and once you get down to 0, like, there's no more energy left. That is a absence of temperature. So that would be something that would be considered a ratio variable, which we'll talk about in just a second. The big differences between these is when you're looking at the different types of calculations you can do between two different values, right? So for these one, because just because something goes from, say, 0 degrees centigrade to 100 degrees centigrade, and then I have something that went from 0 to 200, that doesn't mean that it's double in temperature, because that 0 point is kind of arbitrary. It doesn't really mean anything. Versus if we're going to be looking at something like Kelvin, where that actually is, the 0 point does make a difference there. Does that kind of make sense? Okay. So a good example of this is if you were looking at different temperatures, and I don't know why they pulled this data in particular, but they were doing resting body temperatures of a couple different types of animals. So you can see here, I don't know how, dogs, canaries, and platypus, maybe this is an Australian study, I don't know. But you can see here how you graph the data can be kind of misleading in some circumstances. So with having body temperature done in centigrade here, you can see that by looking at the same exact data and how you're going to graph that, you can kind of get some misleading results. So if you were to look at between A and B, which one kind of shows more dramatic changes in temperature between the two different animals? B looks much different, right? And what's really the only difference in B?
The set point at 25.
Yeah, it's a scale. So when you're looking at a smaller scale, it's easier to see those differences there, right? And so you would say that, oh, the canary has 3 times the temperature of a platypus. That doesn't really make any sense based on the temperature you're looking at. So what's easier to do, or more representative, is if you put it on a kind of a scatter plot like this, where you can actually just see kind of the relationships between them, but you're not actually looking at ratios of values between the two, right? So those are called the interval variables. Then we have the ratio variables, and these are going to be better because, or not better necessarily, but these are going to be ones where you can actually make comparisons and actual ratios between two values. So again, the 0 point is going to be meaningful here. If you have 0 body weight, you have no weight versus if you have 100 kilograms, and then you have someone who's 200 kilograms, that's twice the weight, right? So you can make those kind of ratio decisions there. And so we'll look at a graph in just a second here to kind of show you the different ways you can look at kind of categorizing and collating the data. So looking at this, we can see here that you'll have your different scales of measure. So you have your nominal, ordinal, interval, and the ratio continuous variables. So the last two there are continuous variables. And you're going to be looking at different ways you can compute data from that. And so first thing we'll look at is a frequency distribution. So what does that mean to you guys, if you had to guess?
Like a scatter plot, kind of, where data clumps up.
Yeah, it was just like a measure of the actual frequency of the different things. So for instance, if I were to do a frequency distribution of, say, male versus female, what type of scale would that be? Would it be nominal, ordinal, or continuous? Yeah, so it'd be one of those dichotomous binomial or nominal variables, right? Because there's no inherent difference in between male and female. It's just they're two different categories, right? So if I were to do, I could do a frequency distribution in this room, and I could say there's so many females and so many males in the room, and you can do that. You can basically do this with any of those scales. It's basically just calculating the number of values that you have for a particular category or particular value. Then when looking at medians and percentiles, so when I say median, what does that mean?
It's a single point that's in the middle.
Yes, the middle value for a given set of data. We'll talk about it a little bit more later on, but basically, if I were to look at, say, all of the ages of you guys in the group, and I were to put them on a graph, the median value would be the one who's specifically right in the middle. And that's kind of like the 50th percentile, where you know that 50% of the values are going to be below that, 50% of values are going to be above that number, right? So for that, you can't really do that with nominal data, because you only have two different categories, but there's no real magnitude or difference between them from a numerical standpoint. So you can't really do things like median values between them, because in a lot of cases you'll have dog, platypus, canary. That doesn't make any sense there. Versus if I was doing on an ordinal scale, say you were doing something like a Likert scale for measurement of how boring you thought stats was, from very boring all the way up to super exciting on a 5-point scale. You could look at the median values there. I could look to see, like, based on the frequency of each value that you guys would input on your scale, I can see what the median value is. So that makes sense. You can do the same thing with continuous variables as well. I can look at adding and subtracting values. I can do that with interval and ratio with my continuous variables. You can't really do that with ordinal data. And why can't I do that with ordinal data? You can't.
First plus second doesn't equal third.
Yeah, exactly, because the magnitudes between values don't actually mean anything. So if you do like a 5-point scale, or you saw that poor, fair, good, because those differences there, the magnitudes are different and aren't well defined, you can't really add or subtract those values. Versus if you're doing continuous variables, they're integers. You can subtract one A from B and get C, and that will make sense throughout the entire scale. Again, looking at ratios, you can really only do that with the ratio variables, because again, the 0 point does matter there. And then when looking at, we'll talk about means, what's another name for mean?
Average.
It's our average, right? So how do you calculate average?
Total added up, divided by the total number.
Yeah, so add up all the values, divided by the number of observations, and you get your average. So you can do that with continuous variables. You can't really do that with ordinal or ordinal or nominal variables. And then we'll look at standard deviation. We'll also look at standard error of the mean and kind of what that talks about in regards to the mean. So those are really going to be more reserved for continuous data. And then coefficient of variation, that's going to be more related to ratio variables. Again, we'll talk about that later on in this section. So just be aware that not every scale or not every categorization is going to be useful with particular types of measurements. And so it's important to keep that in mind, what those are going to be useful for. Okay, so how do we graph continuous data? We're mostly going to be focusing on continuous data because, as you might imagine, that's probably the main thing you're going to be seeing in the medical literature, right? Most are going to be looking at things like changes in blood pressure, changes in quality of life, and different continuous scales versus a lot of nominal or ordinal scales. You still will see them every once in a while, but we'll look at how to graph the continuous data here. So again, they're going to be continuous in nature. There's going to be a set magnitude between the different values here. And again, the best way, or in a lot of cases when you're trying to kind of visually represent that data, is to graph it. So we'll look at some of the common ways we can do that. We'll talk about some of these values first, though. So the first thing we're going to be talking about, and a lot of the slides we're going to see coming up are referring back to this data from this 1992 study that we're looking at body temperature. And so I'll kind of reference back to that as we go forward. So you'll see that in a second. But anyway, so calculating the arithmetic mean, which again is just getting the average. You guys already know how to do that. You just add up all the values, you divide it by the total number of observations, and you get your average. Pretty easy. So in this case, this is a subset of 12 patients out of that group of, I think the original number is like 130 patients. They're doing the resting body temperatures for them. In this case, you just add all these up and then divide by?
12.
Yeah, you divide by 12 and then you have your average number there. Perfect. So again here, the smaller subset, the average came out to be 36.77. We'll see how obviously if you take a subset of patients, is that going to be the same average as the larger population? Maybe not, maybe so. Hard to see. We'll have to look at that and see. Depends on how you sample that, those 12, how you pick them out. Perhaps you get a subset of patients who are higher on the scale or lower. It just all depends, but we can see how the averages will change a little bit as we move forward. One of the big things to focus on here when you're looking at averages is the effect that outliers have on the average. And so when I say outliers, anyone know what that means?
Something that's outside of 2SD.
Extreme.
Yeah, so extreme values is either on the high or the low end of the scale. In means or averages, are they sensitive to or not sensitive to outliers?
Yeah, sensitive to outliers.
Yeah, they're very sensitive to outliers, absolutely sensitive. So that's important to remember, is that because I can have, say for instance, we had, say, a 100-year-old patient that came in here. I was doing an average of ages of PA students, and we had, a really late bloomer, 100-year-old patient came in here. She's going to skew the data. She's going to skew that average because, most of you guys are probably in your 20s, and so a 100-year-old person is going to change that data quite a bit, right? Now, if you're looking at larger sample sizes, are outliers going to be easier or less easy to change the average?
They have less of an impact.
Yeah, usually they'll have less of an impact because again, as you increase your numbers, you're more likely to closely approximate the population average, and so you'll find those outliers are less frequent in those cases. And so again, remember that sensitivity we'll talk about in the median in a second, which it doesn't really remain sensitive to outliers. And again, when we're talking about the mean, this is basically our way of quantifying the middle or the central tendency of data. There are other ways to do this, as we'll see in a second, but this is one of the main ones you're going to be seeing. So again, this is just saying that if I have a range of data, this is kind of the central middle point that everything is kind of averaging out towards. Okay, and so the central tendency is going to be really important when we're talking about things like standard deviation and calculating our confidence intervals and things like that. So the median, as we said, is just the middle value. So again, just line up everything from lowest to highest, and the one that happens to be right in the middle is going to be your median. If you have two that are kind of splitting the median, then you would just go ahead and take the average of those two, and that's going to be your new median. So what effect does outliers have on the median?
Much less.
Much less. It still has a little bit, right? Because you're still kind of ticking it one direction, one value either way, but it's much less sensitive. So even if I had, say I was averaging all you guys out, or I found the median age of you guys, and then I had the 100-year-old student come in, they're not really going to have that big of a change on the median value. The average will change quite significantly, but not the median. Right. So again, just keep that in mind. One of the things that you can do is actually compare the median and your average and get an idea of how the data is kind of being skewed. And very frequently, we'll kind of look at, and ideally, if you're looking at a randomly sampled population, you generally want your median and your average to be about equal. Right. So there may be some variation, but you generally want them to be pretty close. Some other things you might see, a trimmed mean. Sometimes you'll see them kind of sensor data on kind of either extreme. This helps to reduce the effect of outliers on the means. An example of this would be something like Olympic diving. How like one judge kind of throwing the whole results. Do you think we see this very much in the medical literature? Not really. You don't want to really trim results. You don't really want to censor results because again, that could be you trying to skew the data to make your data look better or worse or whatever it happens to be. So generally, we're going to try to take into account all information you have available, even if they are an outlier. The mode. What's the mode going to be?
Most frequent.
Yeah, the most frequent value that comes up. Very frequently, especially if you're looking at very exact numbers, so say to several decimal places, the mode's not very useful because if the temperature was 36.07, you're not going to have too many people that come up with that specific temperature. So the medical literature mode is not really used all that frequently, but if it comes up, you at least know what it is. And again, it doesn't always assess the center of a distribution like the mean and the median do, because you could have the mode be on either side, and it basically has nothing to do with the center values, the central tendency of the data. It just says this one happened most frequently. Okay, so as we were seeing there, looking at error and bias. looking at the temperatures that range for that set of patients, we'll see a graph in a second, range anywhere between 35.7 all the way to 38.2 degrees centigrade. And what you see is that most of that variability there is going to be due to just normal physiologic circumstances, right? So looking at circadian variations, aging, alterations, activity, lots of different things can have effect on body temperature, and most of it's just going to due to normal variability. So even if I were to pull a subset of patients out of that, and it looked like they were significantly different temperatures, chances are it's probably just due to coincidence, right? Because a lot of this is just going to be all based on just happen chance that they are just circling around that mean value. And when we look at that variation around the mean, this is where we're going to get a lot of things like our standard deviations. We're going to get a lot of our information regarding how close to the population average that our data actually is. So here, here's a kind of a scatter plot. You can see how some of this data can be represented. So in the left side, you're going to see that the horizontal axis doesn't actually have any difference here. They're just kind of spreading things out to kind of show you where the values are lining up. Obviously on the y-axis, you have the temperature there. So the left side, you have all 130 values that are kind of being expressed. And then on the subset, that's that 12 that we're looking at. And so you can see here that it looks like the average might be a little different, but it's probably pretty close to that whole average of 130, right? You can see that there. Data is not frequently displayed like this because if you can tell, it looks kind of messy, right? Not super useful to you just by taking just one look at it. So more frequently, you're going to see we'll use these kind of whisker and box plots. I'll show you in just a second here. Again, the larger the data set, the more kind of messy that's going to look, and so the less useful it's going to be to you clinically. So what you're going to be looking at. Maybe these plots I'll show you in just a minute. So again, variation can also come from kind of issues with the actual testing itself. So imagine, if I was doing core body temps with somebody, and then one of the researchers didn't get the memo, and they started doing oral temperatures, right? So that's obviously going to skew my data one direction versus another. Versus if someone started doing temporal temperatures. So again, keep in mind that the measurements have to be correct, because otherwise that can introduce kind of unnecessary variability in your data there. And again, bias can be really any factor that's skewing your data. It doesn't even have to be necessarily preconceived notions from the experimenter. It could really be anything that could be affecting. Could be a bad, thermometer. It could be really anything that could be affecting that, right? So the better way to show this data with this box and whiskers plot here, again, it's going to be better with large data sets. So this way you don't have to show every value. You can kind of show a box that kind of encompasses the majority of it. Here on the one I'll show you, you'll see that the horizontal line is going to mark the median for each group. Again, medians are going to be less or more sensitive to outliers. Less, right? Because the median is just the middle value. That 50th percentile does not really get affected by outliers so frequently. And then you'll also see that the boxes themselves will extend to the 25th and 75th percentiles. Anyone know a different name for those particular percentiles?
Quartile.
Yeah, it's your interquartile ranges. So typically you'll see those boxes being represented as these interquartile ranges from the 25th to 75th percentile. And that basically gives you an idea of basically where 50% of your values are kind of showing up at, right? From 25 to 75%. And then you'll have error bars that will kind of show you where those outliers are, depending on the graph and how it looks. And again, make sure you're reading the legends for the graphs to make sure that you know what they're actually displaying to you, because every graph might be a little different depending on how the author wants to organize the data. So for instance here, if you were looking at, again, before you're looking at the big, kind of massive blob of dots before, you see it'd be nicely condensed into one of these box and whisker plots. So if you can look on the left one here, you can see that the median value is being denoted with that kind of horizontal mark there, and then because that's the 50th percentile, then you can also have your 25th and 75th percentile, your interquartile range being demarcated by the outer outlines of the box. And then for the left one, you can actually see that we're marking off the outliers beyond the 5th and 95th percentile there, right? So those error bars are going to go to the 5th and 95th percentile, and then you have a couple outliers there outside of that. So that's just useful to kind of demonstrate where those outliers are and how many of them there were, versus probably a more common way to see it would just be the one in the middle there, where just kind of encapsulate all the patients. So you kind of know where all your different values are. And then the one on the right is just going to be the same thing, but with the 12 subset of patients. So notice how the interquartile ranges kind of vary there. Notice how there's more variability in that when you have a smaller subset of patients. Okay. So the next thing we'll look at are going to be these frequency distributions. So the thing with frequency distributions, it kind of puts a large number of values into corresponding bins. So instead of saying, we're going to look at every individual value, there's 130 of them, it's kind of hard to look at each individual one. You can kind of coalesce them into boxes. So you may say, everyone from 36 to 37 degrees centigrade is going to go into this box. 37 to 38 in this box, and 38 to 39 in this box, okay? So determining how big you want those boxes to be is important because you want the data to show enough detail, but not so much detail that you're kind of looking at just another kind of amorphous blob, right? And so you'll frequently hear these being referred to as histograms as well. So again, this is the same data we were seeing before. Obviously, this first box on the upper left, the first graph is not super useful, right? Because it doesn't show a lot of data. It just says, okay, well, most people are in the 37 degree centigrade range, but they don't get any more detail than that. Versus the one on the bottom, way too much detail, right? So it's kind of hard to get a sense for where most patients are ending up. Versus if I do the one that's on the upper right, this is based on half centigrade measurements. That's a little bit more usable, right? I can kind of see a little bit better idea of where most of my patients are going to be falling into it. It's kind of that just right in the middle kind of representation there. It's your Goldilocks box. Make sense? So you can, but just by changing your values of how many or how wide the boxes are going to be, the different number of values are going to fit into that. So you can see those changes there. Okay. We can also graph the data to help us show scatter or distribution. So we can look at cumulative frequency distributions. I don't see these too frequently being done in the medical literature. Certainly you might see some of those histograms popping up, especially if it's looking at large bunches of data. But here you're going to see basically a line graph that every value on the y coordinate is going to be all of the values below. It's easier if I just show you guys. Just basically, when we're looking at this, just know that every time you have a tick up in the Y category, you're going to be seeing more of the patients falling into that. So eventually, when you get to the far end, you have 100% of patients falling into that. As you start ticking back and get lower, you can see the cumulative number of values that are falling into that. That kind of makes sense? Again, you don't see these too frequently, but just know that you can see it's cumulative. And again, as you go from left to right, you're having a larger percentage of the number of the patients that are fitting into this. You can also show it by percentages as well. I'll show you a graph of that in just a second that kind of demonstrates that.
By the time we get to 39 degrees, 100% of the people...
Yeah, 100% of people have a value that or less than that, right? Versus when you get to 37 degrees, you can see that probably about half or so have a value of 37 or less. Okay. Again, clinically it's not super useful, but just it's another way to show the data.
When would you actually use that?
I don't know that I've ever actually seen it. So it might be, it's just the researcher. It would be a very particular circumstance where they thought that was the best way to represent the data. But again, it's not something you see very frequently. Usually those histograms are a little bit better because you can kind of get an idea of how, in general, how the patients are kind of lumping up together. Here's another one where, again, you can show it by percentage, so it has a very similar look there. The one on the right would be if you were to actually take it and convert it over into a straight line. So you can see how the changes in the percentages are kind of represented there. Again, not done very frequently. Okay. So some things you want to make sure to be wary of is the term data massage. And it's not just a way to work out your statistical kinks or anything. But a lot of times you can see some of the data either being modified or kind of just changed in slight ways to make it kind of fit a little bit better or to kind of make it show what the researcher wants a little bit better. And so a lot of times, this may be things they're not doing intentionally or with any kind of malice. It's just something, that kind of happens. So some of the things that you can see is things like removing impossible values. So say you're, measuring temperature and all of a sudden you got a patient who measured, at 33, right? So that's a pretty low temperature. May not be an impossible value, maybe something really strange was going on. Usually it's something that usually requires further investigation. So whether or not your actual measurement was done correctly or if there's something else, just in particular going on with that patient. But the example here is if you, there's a satellite that was looking at ozone levels over Antarctica, and it was detecting drops in the ozone layer, or however it was measuring it. But because it detected it as kind of an impossible value, because it didn't think back in the 80s that the ozone layer would be depleted. It just kind of chucked that data, and so we didn't really ever get that information for a long time, or no one was looking at it, so to speak. So again, not removing impossible values, but at least acknowledging them and saying, postulate what you think might have been going on with that particular case, right? So again, being transparent and including all the data available. Sometimes you'll see data being adjusted. If your values are analyzed, that may not always be direct experimental measurements. Sometimes you'll have data that doesn't really make sense, and when you start doing statistical tests on it, you can start to just kind of carry it forward. So again, if you're doing your own measurements and things like that, make sure that the information actually makes sense prior to doing the actual data crunching. And again, if you're seeing something where like, okay, well, maybe I can count it as this outcome, or maybe I can count it as this outcome, having inter-researcher variability in making those decisions can definitely be room for bias. So like a good example of this would be with my research study that I did for my fellowship. So we were actually looking at outcomes in coral snake envenomations that were happening in Florida over, say, like a 15-year time period, and we're looking at actual clinical outcomes based on before and after the antivenom went out of production, right? And so we actually had two different people reviewing abstracts, because the poison centers they take case data and they actually make case files for every single patient that gets called in, and so we're actually having to read through and make subjective or make objective decisions on what the actual specialists were writing into the case and converting it into data. So because we had two different people looking at it, myself and we had this other we had a physician who was looking at it as well, there's room for variability there. There's room for bias where I might have measured one thing as this, you might have measured something different, and there's actual tests that you can do to make sure or statistical ways you can actually make sure that the variability between reviewers is not causing any kind of significant changes there. So just keep that in mind. Having different reviewers look at it can be a potential room for bias. It can be smoothing as well, where they're trying to kind of manipulate the data just slightly to make it kind of fit a curve a little bit better, kind of like the curves we saw previously. But again, really need to look at the data as it comes and not just change it to make it look a little bit better. Otherwise, it's going to be invalid. This is also another important one. So variables that are the ratio of two measurements. So frequently you'll see a lot of things being measured as a proportion or as a ratio. It's really important to make sure that your numerator and your denominator make sense. It's very easy for human error to kind of pop into some of these studies to where you're saying that, especially when you're looking at a subset of patients. So say, your study was looking at 300 different patients, and I decided to look at, 150 of them because they had this particular outcome. It's important to make sure those denominators are being held consistently. So if I'm making a proportion, looking at a specific subset, I use the 150 as a denominator, not the 300 on accident. Because otherwise you can get kind of miscalculations there and show results that may or may not be true. So again, make sure that when you're looking at the studies, make sure the numbers actually make sense. Okay, you can do some of the basic math yourself to do that. And then if they're normalizing data, if they're, say, running something from, like, say, 0 to 100%, make sure they're being really clear about delineating what that 0 and 100% are. Otherwise, there could be room for some ambiguity, and you can make some wrong assumptions there. Okay, so then moving on, how do we quantify scatter? So here's where we're going to talk about our standard deviation. This took me a long time when I was in school to actually get my head wrapped around what standard deviation meant. So hopefully you guys will have an easier time than I did, or I'll be a better teacher than what I had. So standard deviation is essentially the variation of the values that you're receiving around the mean, right? So it's basically just telling you how variable the data is that you have for a particular data set. So again, we use this very widely to express, usually it tells you the difference in the variability about the mean. And I'll show you that it's going to make more sense when you see how it's actually calculated. But essentially what it is that the larger the standard deviation you have, the larger the variability in the values you have around your mean. So small standard deviation means that most of your values were compacted around that mean very tightly, and the large standard deviation means you have lots of variability, and so your values are going to be more spread out about the mean. Okay. So here is an example of a normal distribution curve, kind of your bell-shaped curve you guys I'm sure are familiar with. And essentially what we're going to be looking at here is that you can interpret the standard deviation kind of using a general rule of thumb, that about 2/3 of observations in a population are going to lie generally within 1 standard deviation about the mean. So that means one standard deviation minus the mean and one standard deviation above the mean. Okay, and that makes sense when you look at the actual values here. We'll talk about where those come from. But 34.1 plus 34.1, it's about 2/3 of that, right? So if I were to get a random set of data from you guys, so say I was going to measure your guys' blood pressure, and I was going to be get a mean average of the systolic blood pressure for this PA class, and I were to get the average, the standard deviation would basically be telling me how much variability I have in systolic blood pressure about that mean, right? And so if I were to go one standard deviation below the mean and one standard deviation above the mean, I'd roughly have about 2/3 of your guys' values within that group, right? Everyone else would kind of fall into the outliers. Make sense? So if there's a lot of variability there, the standard deviation is going to be much wider in order to encapsulate about 2/3 of your values. Otherwise, if you guys had very close or very close to the average, the standard deviation can kind of shrink some. And I know that it's even smaller or kind of smaller range in order to get the majority of guys into that group. That makes sense? It's all just kind of demonstrating how much variability you have about the mean. So, and in this case, you're looking at the data we saw previously, that 130 patients. You see that the temperature had that average of 36.82, and when you actually calculate the standard deviation, which I'll show you how we do that in a minute, the standard deviation was about 0.41 degrees centigrade. So that means that about 2/3 of patients fell within the range of 36.82 minus 0.41 and then plus 0.41. So about 2/3 of patients fell within that range. Everyone else is kind of an outlier outside of that. Okay. If I were to go to 2 standard deviations away, so 2 standard deviations minus the mean and above the mean, does anyone know what number that comes out to be? Roughly.
36.00.
Should be about 95%, right? So that'll be really important when we're talking about looking for statistical significance, is that 2 standard deviations away is roughly encapsulating 95% of values, okay? So just kind of keep that in the back of your mind as we go forward talking about this stuff. So again, looking here, you can see the scatter plot for the various values, the 130, you can kind of see them organized. The x-axis doesn't really matter, just kind of doing it for demonstration purposes. But you can see that the average there on the right with the standard deviation either side. So again, we said that the average was about 36.8 some odd degrees centigrade, and then you had that variation of 0.41 either direction. And so notice that if you see that standard deviation, those bars, that encapsulates about 2/3 of the values you can see there. Does that make sense? Okay, so there's even more variability in this data. Say that the ranges, say it went up even higher and lower, you see those standard deviation bars start to grow because it needs that wider range in order to encapsulate about 2/3 of that data. And vice versa, if it was going to go down, you see the standard deviation bars shrink. Okay, so how do we calculate the standard deviation? Like I said, generally it's pretty hard to quantify the variability, but basically what we're doing is we're looking at the distance of each value from the mean. That's both above and below, and then we're going to balance each of those out to 0. So essentially what you see when you're actually calculating itself, and again most of the time computers are doing this for you, you're going to first calculate the mean of all the values, right? So you just get the average, it's pretty easy. Then you'd actually calculate the difference between each value in that data set from the mean. Okay, so then you're going to have an equal number of differences as values that you have in the data set, right? You're going to square each of those, you add them all up together, and you're going to divide that by the sum by n minus 1. And n minus 1 is basically determined to be your variance, and basically n being the number of observations you had just subtracted by 1. And then you take the square root of the whole thing and get the standard deviation. So clear as mud? Again, conceptually, it doesn't make a ton of sense, but when you look at it here, it makes maybe a little bit more. So again, this is the calculation you would do to actually figure it out. So basically, by figuring out the differences between each value and the mean, that can help you to determine how much variability you have in those values from the mean. So again, looking here, if you're looking at one standard deviation above and below, that's where you're getting 68.3% of your values. If you were to go 2 standard deviations either direction, you end up getting a total of about 95%. And if you went 3 standard deviations, you'd encapsulate almost 100% of patients. You may still have those outliers and those values there. You can also have the coefficient of variation. So for ratio variables, this is going to be the variability that can be quantified as the coefficient of variation. And essentially, this is just going to be your standard deviation divided by the mean. I don't see this used too frequently, but the cases where it could be useful is that it's good for measuring the variation between different types of values. So say, for instance, you're measuring blood pressure. Your average, if you did an average blood pressure, what would be the units on your blood pressure?
Millimeters of mercury.
Yeah, milliliters of mercury. If I were to do a standard deviation based on that calculation we saw previously, it retains those units. So usually say a standard deviation of, say, how many ever millimeters of mercury. You saw that with the temperature example, where you saw the standard deviation being reported as 0.41 degrees centigrade. Here, if you were to have two different things you want to measure, say like you want to compare pulse rate versus serum sodium, you can't really do that because it's kind of apples to oranges. But by determining what the kind of the coefficient of variation is between those two, you can kind of make a little bit better connection there. Because here you have the standard deviation divided by the mean, and that's going to give you a percentage basically, or percentage of variability there. So for instance, here, if you had CV equals 25, 0.25, it's going to be about 25%. The standard deviation is 25% of that mean, and so then you can compare two different values because it ends up losing the units at that point. So you don't see it used too frequently, but if it does come up, you'll kind of know what that is used for. You can also use the median in order to help determine some of your variability about the central distribution. And so you can have the median absolute deviation is a good way to do this. Again, not something I see too frequently, but good to have at least some knowledge of it. Again, the median being the kind of the center value is your 50th percentile. So 50% of values are going to be below that, 50% are going to be above that. So first what you can do is calculate the median. So you can just kind of rank order the group of data and you find out what the middle value is. And then you're going to calculate how far the difference each value is from that median. Right, so similar to what we were doing, we were with the standard deviation, we were actually figuring out the difference between the mean and the values that we're looking at. And then here is able to tell us basically that variation and the differences between the means, or with the median here. So anyway, so once you get all those differences, so you measure all the differences between from the value to the median, then you find the median of those differences, and then it tells you the median absolute deviation. Basically just another way to tell deviation around that central distribution. Okay, then moving on, we'll talk a little bit about Gaussian distribution or normal distribution. It's kind of what we already were seeing with those bell-shaped curves we saw previously. So you'll see that the normal distribution is kind of the basis for much of statistics. So again, just similarly to what you would see where if I were to flip a coin 50 times, I'm probably not going to get 25 heads and 25 tails, right? Just because random happen chance, I'm probably going to get some variation of that. But if I have a million people do 50 flips, I'm much more likely to get kind of that central distribution where I would have closer to the average of being a 50-50 chance, right? So the idea here is that when you do a random subset of a patient group or a population, they are going to be representative of that population, and that everyone's going to kind of regress to the mean with the population. So everyone's going to have a population average, and we can't figure out the population average because we can't measure a value in every single person in whatever your group is, but you're at least going under the assumption that your random sampled group is going to be representative of that population, and that we have some values we can look at to see just how close that mean or the average of my sample is to the population, right? So that's going to help us to determine a lot of things, especially with looking at confidence intervals, looking at being able to make inferences about our sample to the population, things like that. So the normal distribution is an assumption that we're making whenever we're looking at a random sampling of patients. So, and again, when you're looking at things like, random factors tend to cancel each other out when you're looking at sufficiently big enough population. So you'll see that, extremes tend to counteract each other on either side. Eventually you're going to get kind of that central mean that is, you'll end up having that bell-shaped curve that occurs there. Again, normal distribution, Gaussian distribution, again, this is an assumption we're making, and like all assumptions, most of the time it's not going to be 100% true. Talk about the importance of that in a little bit. Here's the extended bell curve, if you're ever curious what was on the other side of that. Yeah. Okay, so again, the next figure is going to show the ideal Gaussian distribution. Again, the horizontal axis shows the various values that can be observed in that group. Vertical axis just quantifies the relative frequency that was measured in that group. And the center is going to be the mean. right? So every time you see the center in that bell-shaped curve, that's the mean value for that sample. Again, standard deviation is going to be the measure of variability in the data around that mean. So smaller standard deviation, smaller variability around the mean, larger standard deviation, larger variability. And basically the entire area under the curve should represent the entire population, right? And we said when we went one standard deviation away in either direction, we have about what percentage of the population? Close to like 68%, so around 2/3 or so. And then if you go 2 standard deviations out, you should get 95% of the population. Perfect. Yeah, so and then 3 standard deviations get 100%, almost 99.7 if you want to be specific. But anyway, so this is just in general when we say a Gaussian distribution. So again, if I were to look at, say, blood pressure, systolic blood pressure for the entire U.S. population, I would probably end up getting something that was very close to this, right? May not be 100% accurate, but it should be pretty darn close to having a Gaussian distribution. Because again, if you sample enough people, the extremes are going to start to cancel each other out as people tend to regress towards the mean, right? So very frequently, you may not have all the actual data available in the medical, in a particular journal article, but very frequently, if they're making the assumption that they have a normal distribution and you have the mean and the standard deviation, you can have a pretty good idea based on what that data is actually going to look at. Because again, if I know that the average blood pressure was say 120 millimeters of mercury systolic, and I have the standard deviation, I can figure out what 68% of the population had their values between, and if I went 2 standard deviations out, I can figure out what values 95% of the population had their blood pressure at, right? So just using those 2 things, you can kind of tell a lot about the data if you're under the assumption that's a normally distributed set of data. So again, when we were looking at those graphs, like you notice that we frequently you plot the mean at the 0 point, and then you're going to look at your standard deviations at intervals of 1, 2, and 3 out from that. And so very frequently you can use these z values, which in particular, say you have a particular value in your data that came back. So say you were looking at blood pressure and the patient's blood pressure came back at say 130 systolic. Having that value and knowing what the mean and the standard deviation is, you can get the z value basically. It kind of tells you how far away they are from the particular mean. This doesn't get used all that too frequently, but just kind of helps to kind of inform you when we look at things like the 95% confidence interval, where this is kind of coming from. And so based on that, there's a number of z values that get generated from this. And so for instance, when you look at the z value being 1, again, that's 1 standard deviation, you know that when you're going from negative z to plus z, you're going to be getting standard deviation about the mean of around 68% of those values. Then we go 2 and 3, we kind of talked about what those values are already. Just keep in mind that the normal distribution does not necessarily define normal limits of things. Again, normal is not going to be the same meaning as you would see with talking about patients and things like that. So again, just realize that typically patients will kind of center around a particular mean. Just because it's normally distributed does not mean, because if you're selecting for a subset of, say, septic patients, obviously their temperature is not normal compared to a normal healthy individual. So just keep that in mind, that the normal distribution is really referring to your subset of patients and what kind of population you're generalizing that out to, and not necessarily the normality of the values themselves. Okay, the next thing we'll look at is going to be the standard error of the mean. This is going to be the ratio of the standard deviation divided by the square root of the sample size. Otherwise known as the standard error of the mean. So what basically the standard error of the mean is telling us is how close our mean is, the value we have as our average, is to the population average. So it kind of gives us some degree of error in that. So again, you can see here that you just take your standard deviation divided by a square root of n, which what is n? Yeah, it's your sample size, your number of observations you have there. And again, it's not really telling us directly quantifying scatter or variability of the data. It's just telling us how close our data is to the actual population average would be. So say for instance, what effect is, if I increase my sample size, if I increase the number of observations I have, what is that going to do to my standard error of the mean?
Make it small.
Should make it a lot smaller, right? So you can end up having, as you increase sample size, as you get closer and closer to that population number, you're going to see your standard error of the mean is going to get smaller and smaller as you get closer and closer to the actual true population average. So again, if I was dealing with a small sample size, that makes my standard error of the mean larger or smaller. So small sample sizes, so I'd be driving down my denominator, to make my standard error of the mean larger, which means that I'm probably farther away. There's more chance that the average I have is not specifically the same one as the population. So it really is just telling us how close to the population average we're actually getting there. And the bigger sample size is going to get us closer to the actual population value. I'm just going to finish up this topic and then I'll let you guys go. So again, this is not a measure of the spread of the actual data you're having, but again, how well you know the population mean. And your SEM, or your standard error of the mean, should always be smaller than your standard deviation. So if you get something bigger than that, then you should probably figure out your math. And again, a smaller one suggests you're actually closer to that population average. And then we'll actually use the standard error of the mean to help us calculate confidence intervals, which are going to be really important when actually looking at the results of data and looking to see, looking at comparative results of different interventions we'll see in the literature. Okay, I'm going to cut it here, and then we'll get started probably tomorrow.